He is an assistant professor there, has been there 2 years. He got his PhD in 2009 from the University of Washington. And he's had a fairly successful career, many awards and so forth, including the Andrew Mellon Foundation Award for Technology Collaboration and the MIT Technology Review Top 35 Innovators Under 35, which you see in there in the magazine once a year. And he's had several Best Paper Awards. And I was interested in inviting him because I'm interested in HCI. We don't see enough of that in our department. And also I'm interested in healthcare, and this connection to disabilities I thought was interesting. And so I'm sure it'll be fun. And please ask questions, right?
Yeah,
okay.
Please interrupt me. All right, well, thank you, and thank all of you for coming. I've had a great visit so far. I am Jeff Bigham from the University of Rochester, where I lead this group called ROC-HCI there at the university. So today I'm going to be talking about my research, which is in human-computer interaction. My background is kind of in artificial intelligence, or it was, and I found HCI as a way to kind of allow me to get done what I wanted to get done. I wanted to help people interact with information better. I wanted to help them, I guess, in the real world, in their everyday lives. And in particular, a lot of my work is motivated by helping people with disabilities lead more independent lives, better interact with what's around them. And so today I'm going to be talking about, in particular, some work my group and I have been doing around the idea of real-time crowd support. And so this talk is going to be a mix of motivation and history, and also a bunch of projects that we've been working around this theme. So it turns out that people with disabilities have relied on assistance of others in their community for centuries, right? So a blind person may ask a fellow traveler the number of an approaching bus, or a person with a motor impairment may ask somebody for assistance, so getting something off a shelf. Individually, a lot of the challenges that people with disabilities face are actually pretty small, but if you put them in, if you collect them together, they can lead to lack of independence and bigger problems. It turns out also that despite many of us thinking maybe in this room that this idea of crowdsourcing or human computation is kind of a more recent phenomenon, people with disabilities have been soliciting the assistance of others for a very long time with structure around that assistance. So for instance, volunteers may go to a person's home to help a blind person read their mail. Sign language interpreters here can help convert spoken speech into sign language to help a deaf or hard of hearing student follow along in class. And recently, technology has even been applied in this space. So things like video relay services, which allow a deaf person to actually make a phone call. And the idea then, the deaf person is actually communicating over Skype or something like Skype, and a person they call is then actually making the voice call. And so this is pretty fascinating. And what I think is really interesting is that connectivity has really allowed us to engage the crowd in new ways. It allowed us to form new crowds that may provide a new route to assistance for people with disabilities. And so just to kind of talk just briefly about kind of the broad nature of what I think of as the crowd. This varies everything from services we might think of in computer science, especially of the crowd as things like Mechanical Turk, so these micro-task marketplaces where you can pay people small amounts of money to do jobs for you. And it turns out that Mechanical Turk is not alone in this space anymore. There's a whole slew of startups that are doing this, things like Crowdflower and others. There's a bunch of people who are actually, if given the opportunity, would be willing to volunteer to help somebody out, especially for a good cause. And because of the connectivity, that means that I am always connected to everyone else via my phone. Maybe I can actually harness the few seconds of time I have, the few minutes of time I have waiting in line, or sitting on the bus to help somebody out. And then our friends and family are also really easily connected to us by social networks, Facebook, Twitter, things like that. And so a lot of people have been thinking about how to engage the crowd, how to solve problems that are too difficult for computers by engaging the intelligence of people. What I think differs about the research that I've been doing at the University of Rochester is that we've really been targeting this idea of real-time human computation or crowdsourcing that's interactive. And so this means that we can build tools that we'd like to be maybe eventually done with automatic technology, so intelligent user interfaces, but today in a deployable way by engaging people in real time. And so this is hard because of crowds. Crowds are interesting, and the way we think about crowds are they're this dynamic group of people. So that means people come and go, and recruiting workers to do your job can actually be kind of slow. If you think about Mechanical Turk, it actually takes a while if you post a job to get somebody to come to do it. And crowds are unreliable. You never really know who is part of that crowd. For a whole variety of reasons, they may not provide the great level of assistance that you would like them to. And so we need to build models that allow us to take kind of these messy crowds and extract out the good parts of them, so the intelligence that these crowds contain, and while still making guarantees about the quality. So I'd like to take just a second to talk about who would be part of one of these crowds. So how many people here have actually gone on Mechanical Turk and done jobs? Nobody. All right, how many people have answered a question on the social network? Yeah, come on, you've all probably done this. All right, well, so maybe we're outliers, maybe we're afraid to raise our hands. But I would just like to kind of, this chart is going to, as I add things in here, is going to kind of illustrate to me why the promise of crowdsourcing, because it turns out we actually have a lot of time. Okay, so this data is actually a little bit old, but the relative scale is going to make sense. So at one point in time, Twitter had about 80 million people using it. I'm actually pretty active on Twitter, and so there's all kinds of time I'm wasting there. Facebook, of course, is much greater than this. I couldn't even, if I drew the correct scale, it would be up through the ceiling. But what surprises a lot of people is actually this next piece of this chart, which is Farmville. Just coming in right below Twitter. So I don't know if you've played Farmville, but this is a game made by Zynga. And essentially, you, for free, are able to have your own virtual farm. And this game is so monotonous and tedious. Zynga actually makes huge amounts of money selling you ways to get around the tedium of playing Farmville. But it's actually a very addicting game. A lot of people play this game. And they've done a really great job of kind of making this a social experience, so you can actually have friends on Farmville, and they can have neighboring farms. You get all these little rewards, so like if you have enough money that you earn by cashing in your virtual crops, you can get these rewards like little houses and new tractors and all of this great stuff. So obviously people, if you make it fun for them, are willing to spend time doing work. Wouldn't it be great if we could harvest that work? Regardless of who you are, regardless of your expertise, you spend a lot of time really just waiting, right? So here is a line at a DMV. What I like about this picture is you can imagine these people. Maybe they're not skilled workers, but maybe they're doctors, right? Maybe they're rocket scientists. Maybe they're computer scientists, even better, right? And here they are just wasting their time in line. So a lot of people have time that's not even being used. And just one final example. Time adds up. So this example is a few months old now, but the iPad 2 came out a few months ago. And there were reports about this fancy new cover. And what this cover did was you didn't have to, once you opened up the cover, slide to unlock your iPad. It would just unlock automatically. And so that saved you 5 seconds, right? Well, man, if you could just imagine, if you took 5 seconds and you assumed that somebody made an estimate, this is about 6 minutes a week if you use your iPad a few times a day, and they're projecting to sell 40 million iPads in 2011. Well, that's 40 million hours approximately of time that's just being wasted. And you might say, what in the world could you possibly do with 5 seconds? Well, people have already figured out how to harvest 5 seconds. This is reCAPTCHA out of CMU. And the idea is that instead of just solving a CAPTCHA and having that work wasted, you actually help to OCR documents that are too difficult for automatic OCR alone. So automatic OCR and then human OCR based on reCAPTCHA. So there's a lot of potential in the crowd, and it's a lot of time that all of us have that we might be able to harness in good ways. All right. So that was kind of my introduction to people with disabilities, having used human assistance for a long time, the potential of human computation, and why many of us, even if we think we don't have time, might actually participate in it. So the first project I actually want to talk to you about that we've done at the University of Rochester is on usable CAPTCHAs. And so this is actually, in particular, not just targeted at regular CAPTCHAs, but audio CAPTCHAs. All right, so probably most people in the room know what CAPTCHAs are. They're these problems that are designed to be difficult for computers, but relatively easy for humans. Most common instantiation of these looks something like this, where you have some text that's somehow obfuscated, and the task that you have to do to show that you're a person is to figure out what text is in these CAPTCHAs. The initial ones that look like this, these visual CAPTCHAs, required vision. And so obviously this excludes people who are blind. And so not long after the visual CAPTCHAs were introduced, people introduced audio CAPTCHAs. And the idea with audio CAPTCHAs is pretty much the exact same thing, where you have some text or characters or numbers, and you distort them in some way to make them difficult for computers to pick out, but hopefully still easy for machines to pick out. And so what I have here is essentially a test for all of you. I'm going to play an audio CAPTCHA, and you just listen to the audio CAPTCHA, and I'm going to later ask you what it says. So here we go. 3, 2, 1.
1, 7, 8, 2, 3, 4, 8, 5.
All right, so did anyone get that? How many digits do you think was in that audio CAPTCHA? 6 or 7? 20? No. There's actually 10 digits. So and it turns out the problem with audio CAPTCHAs is not just to identify how many digits there were, it's actually to identify the digits that make it up. So I'm going to play it one more time, and this time I'll animate those digits just to convince you.
1, 7, 8, 2, 3, 4, 8, 5.
So audio CAPTCHAs. And just, again, this is not an unusual audio CAPTCHA. This is actually the Microsoft audio CAPTCHA that used for a number of years. So a couple of years ago, we did a study of these audio CAPTCHAs and also visual CAPTCHAs. We took 10 examples from 10 different audio and visual CAPTCHAs. We had a bunch of blind people and a bunch of sighted people attempt to solve these CAPTCHAs, and here are the results. So essentially, the first try results are here, where it took blind people were about a little over 40% successful at solving the audio CAPTCHAs. Sighted people were about the same on the audio CAPTCHAs, a little lower, but yet sighted people were about twice as successful at the visual CAPTCHAs. So this probably doesn't surprise you, given that you've just heard one of the audio CAPTCHAs and probably found it pretty tough. But when we started talking to people, and so we did this study to kind of get a quantitative comparison, but then we started talking to the people, the blind people who participated in the study, to ask them about their experiences solving audio CAPTCHAs. And not surprisingly, many of them said, I hate audio CAPTCHAs because they're hard. But many of them also cited the user interface that was provided to them to solve the audio CAPTCHAs as a big challenge. And so to get a sense of why that might be, I'm going to play a video here of audio CAPTCHAs, an audio CAPTCHA being solved with a screen reader. And so essentially what's going to happen is this is going to start playing. It's going to read these instructions, and then the person in the video is going to solve the audio CAPTCHA. So here we go.
The audio file is intentionally distorted to prevent automated programs from reading it. D. If the file plays in another program, remember the numbers, return to this page, and then type them in the field below. Play audio button. Browse off. Play audio button. Audio number, edit box. Browse off. Numbers you hear, edit box. Question.
Okay, so you might have gotten a sense from that why the interface was actually getting in the way. When the audio CAPTCHA started playing, of course, it overlapped the audio of the screen reader, which was the interface the user had to the window here to solve the audio CAPTCHA. Fortunately, someone there, again, not to pick on Microsoft, but to pick on Microsoft, someone thought of this problem and gave a helpful hint about how to solve it. And that was just remember the arbitrary sequence of 10 digits when the audio plays, and then type it in the box later. You can imagine it's a little difficult to do. All right, so we simplified the interface. Basically, you had one box. You press a period in that box, it starts the audio CAPTCHA playing. The advantage of this is that you're already in the box, so you don't have to do any of this navigation. There's no boxes that pop up. And you're just right there and ready to type when the audio CAPTCHA started playing. We redid our study, and just from this simple interface change, users had a 59% higher success rate on audio CAPTCHAs without changing the underlying audio CAPTCHA, without changing anything, therefore, about the security of those audio CAPTCHAs, but just by changing the interface. We took some lessons from this. Usability is more than accessibility. It's possible that a blind person could solve the other one, but that doesn't mean that they were going to be able to. And interfaces just can't be naively adapted. So maybe some general lessons that people could take away when they're designing interfaces for blind people. But just to continue with this idea a little bit further, what do people do if there's no audio CAPTCHA? So I was kind of presenting this whole work like audio CAPTCHAs are very popular. They're getting more popular. reCAPTCHA has an audio version, for instance. But a lot of websites just don't have audio CAPTCHAs. So what do you think blind people do when there's no audio CAPTCHA? Well, they ask friends around them to solve the visual CAPTCHA. And so I think this is neat, and I think this leads very well to the next project that I'm going to talk about, which is VizWiz. So just as I was thinking about problems that computers have a difficult time solving, but humans are good at, led to CAPTCHAs, right? So to be able to differentiate the two. This same line of thinking actually led Luis van Ahn and others who were some of the pioneers of this idea of human computation to think about, well, maybe we could actually engage people as part of computational processes. And so VizWiz is one example of where we're doing that. And this is an iPhone application that we've developed that allows blind people to take a picture, speak a question, and they then get answers back in nearly real time from the crowd. Okay, so essentially we're solving visual questions with the crowd. And so one question you might ask is, well, why do you need to do that? There's all of this great technology that's been developed over the years to solve visual problems, right? So there's optical character recognition, there's color recognizers. I guess I have speech recognition on here as just one example of another technology that interprets sensory information. But there's big problems with this technology. It's very limited in scope, so your OCR program might be able to work pretty well on a really high resolution version or picture of a scanned document, but it's probably not going to work once you give the camera to a blind person who takes a picture of a street sign. It has unacceptable error rates, right? So even something as simple or seemingly simple as a color recognizer actually trips up pretty substantially when used in a real situation. If I took a picture of my shirt, what color do you think a color recognizer would say? If I took a picture, here's my jacket. It's actually one color, right? Took a picture of this. What do you think it would say? Well, unless I really carefully framed it, and even when I did, there's actually a lot of colors that kind of make up this shirt, so what do you choose? But a real picture would be something like this, right, where I have a little bit of the shirt and a lot of background, so it's actually pretty tricky to get the right answer. The technology that's available tends to be really expensive. This is a mobile OCR phone from Kurzweil. This cost, I think it was $1,000 for the OCR software to run on this phone, plus $500 for the phone. This is not atypical of assistive technology. And in general, I also argue that this technology isn't exactly what people want anyway. And to get a sense of that, I have this big giant menu from a brewery. So imagine we had an OCR program that could reliably pick out all the text in this menu. It'd still be pretty hard to ask questions that we might actually want to know about this menu. So it wasn't long ago that I was a graduate student. And one of the things I would normally look for when I was a graduate student is what's the cheapest X? In this case, what's the cheapest burger is what I'm going to ask. If you just had a big long stream of text, it would actually be pretty difficult to answer that question. Now, it turns out that the answer is right there. It's still kind of blurry, I guess, but it's called the No Frills Burger. I think it's $7.95. And if you're sighted, you can find this information pretty quickly. You're using all kinds of clues. You know, you're able to scan this outline that's provided. You're able to look, see that says burgers. Well, probably the cheapest burger is under burgers. It doesn't take a genius to do this, but yet our automatic programs are unable to do this, at least not in a general way. And so that's why we thought it might make sense to engage the crowd. And so again, VizWiz is very simple. Basically, blind people can just take a picture with it, speak a question to their phones, and then they get multiple answers back from the crowd really quickly. And you might wonder, how does a blind person use an iPhone, right? So this might seem interesting. We actually did some work on this when I was a PhD student back at the University of Washington on accessible touchscreens. And some of the ideas from that work actually made it into every iPhone. So now all I have to do is triple click on my phone.
Voiceover on. 438.
Now I can
slide to view.
use my phone even if I can't see the screen, although I'm not very good at it, so I keep peeking.
One up compass, maps, music, mail, calendar. Choose.
All right. And it's actually very interesting, the types of things you can do with a touch-sensitive surface. We don't really care about the screen if we're talking about non-visual interfaces, that are really difficult to do if you are restricted to physical buttons. That's a different story for a different day. And so just to give you an idea of some of how this really works in the real world, I thought I would show a video. And video. What's pretty fascinating, kind of fast forwarding, is that we actually released VizWiz out on the App Store. A bunch of blind people started using it. And this particular person actually thought it was cool enough that he, independently from us, actually recorded a video of him using it in some common scenarios. And so I think it's fascinating because here's a real user really using it. And you get to see a lot of things about how he interacts with his iPhone, and then also how he takes pictures, which is another thing. How does a blind person take a picture? So assuming this works. Wait. Oops. Well, somehow it should work.
I'm going to do a quick demonstration of VizWiz for the iPhone. Well, it's really for iOS, but I have an iPhone 4. I'm going to show you a couple common household things that I tested VizWiz today with, and or tested VizWiz with today. And I just wanted to kind of show you some of the results. I'm pretty impressed. So I've got my thermostat here, and I've set it way down, and I'm going to take a picture here. So I'm going to place this, move it back a little bit, take a picture. I'm going to record my question. What does this thermostat say? I have some options as to what sources I'm going to pull the results from. I'm going to select web workers and IQ engines, and so I'm just going to go ahead and send.
Please wait while your question is sent.
So it's going to send my question. So web workers will actually pull information from human sources. IQ engines, I imagine, pulls it from image databases, somewhat like Google Images. You also have the option to pull results from social networks. I think Twitter is the only option here now, but on the website for the application, they talk about Facebook being an option. So let's see. It already has some answers available.
Thermostat, 5 engines.
The IQ Engines has it labeled as a thermostat, so we knew that. That doesn't do me too much good if I wanted to get a temperature reading. So if we just hold on here for a couple more seconds, earlier I got a result probably within 45 seconds, so just hang tight here. It did identify the temperature earlier. Okay, a web worker said that 75 is on the left and 71 is on the right. They're not sure what the current temperature is. I can tell you that 71 is what I have it set at and 75 is the current temperature. Is that correct?
Yes.
All right. So we have 2 pairs of eyes that say that that's correct. So, all
right, so that's just a quick example. He goes on to some other scenarios, telling what color his shoes are. He wants to match it with his outfit, and a few other things. I think a lot of this video, I think, is pretty fascinating. I mean, you got that sense of how a blind person would use a touchscreen, how they take a picture. Some of the interesting qualities of the answers already you see in this video. So 71 on the left, 75 on the right. I'm not sure which is the right one. Imagine, building a automatic question answering system that could give you that kind of an answer, right? So to be able to express, not only be able to do OCR in general, but be able to express a confidence like that. Let's see. So just a little bit about how this works. Essentially what happens is these questions are forwarded to our server. They go out on our web page. We recruit workers. We actually recruit multiple workers. So the user takes a picture, asks their question, and then the answers go back. And again, we get multiple workers, and there's a number of reasons for that, but they all relate to these qualities of the crowd that we expect. So crowd workers will take varying amounts of time to answer the question. They may or may not answer the question correctly. In this case, we've actually made the choice of not trying to verify that the answers are correct, but letting the user do that, and instead returning multiple answers. We do this for latency reasons. So if we try to verify or somehow validate that each answer was correct, that actually adds time. And so we feel it's much better to let the user figure that out.
Is there guidance that you give to the crowd? Like, if you're not 100% sure, say that, or give more detail?
Yeah. So I'm not sure if there's this little paragraph you can't really read here. It says unable to answer the question. It kind of gives them feedback about what to do, because exactly, as we'll see through some more examples here, a lot of times you can't answer the question because the photo isn't of the right thing, or it's too blurry, or a number of other things. And so we give the crowd some instructions on that.
So you translated their spoken question into text first?
So we try to do that. This says, which can is the corn? So speech recognition doesn't always work, and so we also just play the audio here. I don't have the chart in this slide deck, but it's kind of interesting. If you look at a breakdown of questions, the answers come back the fastest when the speech recognition works, so they didn't have to listen to the audio, and actually when the question was answerable, right? So workers get a little bit nervous about answering something if they can't, which kind of makes sense. So what I think is fascinating about this is that this is essentially an example of deployable Wizard of Oz, right? So in HCI, we also often kind of talk about this idea of a Wizard of Oz study, where instead of going right off and trying to build all of the complex algorithms and AI and everything else that might go into a system that might do something useful, instead you kind of put people behind the curtain to control the system, let people try it out and see if it's actually useful, right? So before you go to all that effort. And so with things like Mechanical Turk, with the crowd, we can actually build systems that are essentially Wizard of Oz, but are also deployable. And so I have this cute little animation of the wizard going into the phone. So VizWiz is kind of an example of this idea of deployable Wizard of Oz. Before we released it on the App Store, we did this initial field deployment with 11 blind iPhone users. And I have these examples here of questions that they really asked. And so I like these because they kind of illustrate the diversity of questions that are asked and kind of hint at why it would be really difficult to make something automatic that could solve all of these. So the first question is, what color is this pillow? First person says, I can't tell, probably because the picture is kind of bad. And the next person says multiple shades of soft green, blue, and gold. Pretty interesting answer. What denomination is this bill? 2020, people get that. Do you see picnic tables across the parking lot? So people trying to get a sense of space. So no technology really helps people answer that now. Both the questions are no, or both the answers are no. What temperature is my oven set to? So there's all kinds of appliances which have inaccessible interfaces. Can you tell me what this can is? You can tell this picture was taken by a blind person. It's actually the back of the can, right? And now, nevertheless, right, the people are actually able to answer this. It took them a little longer than the other ones. They say chickpeas, beans, and Goya beans. Now, it turns out that the primary ingredient in chickpeas is actually chickpeas. So you can tell from the ingredient list what this is. What kind of drink does this can hold? It might not be obvious that there's anything here, but it's actually a little Red Bull can here. So people said energy or energy drink. So I think this is interesting. It kind of gives you a sense of the types of questions people wanted answered and the kind of answers they get. We did a lot of work to try to get these answers back quickly. And there's a number of ways that of strategies we used for these. I'm going to go over just two of them. One is, if we think about how tasks on Mechanical Turk are completed, there's some amount of time it takes workers to be recruited. And then it takes them some amount of time to actually do the task. This should be pretty obvious. So an easy thing you can do is once you've recruited a worker, you can actually have them do multiple tasks. And that way, they're ready at multiple points. And so if a question comes in, they're more likely to be there to answer it. And then you can also recruit multiple workers who will each have their own recruiting time and their own time to complete each task. And so if you do enough of these, recruit enough workers and have them do enough tasks, you actually have a worker ready pretty much any time that you want. And as an added benefit, you might be wondering, if we don't have a question for them to answer right now, what are they doing? We actually have them answer old questions. And so this is kind of an implicit learning phase, right? So they learn what it's like, what to expect. Maybe they read those instructions about what to do if they can't answer the question. And so this actually works pretty well. The other thing that we can do is we can get a jump start on recruiting these workers. And we do that by sending a signal off when the user starts taking a picture before they've actually sent it in. So if someone starts using the app and they start trying to take a picture, there's a really good chance they're going to ask a question. And so we can actually optimistically recruit workers beforehand. So ideally, we can actually get rid of a lot of that recruiting time just by covering it up with the time it takes the person to formulate their question. If we pull out all the stops, and we're pretty aggressive in pre-recruiting workers and all this stuff, we actually showed we could get answers back to people in an average of 27 seconds, which is getting pretty fast, right? So that's about about the point where it's still, believe it or not, it's 27 seconds sounds short. It does still feel like you're waiting pretty long, 27 seconds, but it means that you can actually use it in real situations, right? So you can take a picture of a menu in a restaurant and get an answer back before you leave the restaurant, for instance.
Jeff, do you use Turk, or do you have to incentivize this with paying people, or?
Yeah, so I've kind of made this whole thing nebulous. We use Turk for this study. Now we're doing mostly volunteers, and we're trying to kind of build our own crowd, because especially for this kind of an application, we think that people would want to participate, and so we think that we can actually build our own crowd. And we have a number of people, something around 10 or 20 people, who have volunteered as a kind of a pilot group, and a whole bunch of other people who are kind of on our waiting list who have actually sent me emails out of the blue saying, hey, I want to volunteer. And so we hope that this type of approach of our own crowd will allow us not to have to charge for it.
Just out of interest, how much did VizWiz cost you?
So
per year or something like that?
On average, it was 7.5 cents per question, which resulted in 3 answers, about 3 answers on average. So we did release VizWiz out on the App Store. So here's our page at VizWiz.org. And it's been pretty great to see kind of the uptake by blind people. So we released this on the very end of May. We've had about 2,000 downloads. We keep getting about 200 questions per day. And overall, we've had about 20,000 questions answered. Let's see. So this is kind of a test again. It's a bit of a trick. So some of these pictures come from VizWiz users. Some of these pictures come from one of the more popular computer vision data sets. Your job as the audience is to tell me which ones do you think came from the popular computer vision data sets and which one do you think came from VizWiz users? Well, I don't want...
Crocodile came from user.
Well, so just as one of the implications of this, what we're building with VizWiz is this big data set of real questions that blind people want to know about their environment that we hope to be able to package up in a way that computer vision researchers can use as kind of a challenge. And one of the ways we imagine this working is kind of as this two-stage process. The first process would be basically taking a new question, categorizing it into a subset, so some kind of category. So say color recognition, or getting a sense of space, or object recognition, et cetera. And then maybe eventually being able to solve some of these categories with computer vision. And so it's been fun for us to kind of look at the difference between the pictures that we get from our users and the types of pictures that are used in these computer vision data sets. But you might look at these, and there's some common problems that blind people have taking pictures. Framing an entire object is difficult. Making sure you have the right side of it, getting the object in frame at all is tough. And so we've also been thinking at the same time about how we might help blind people take better pictures. Here's a quick example of helping a blind person take a better picture of a document. So you see a person here with an iPhone getting assistance taking a picture of this document.
Viewfinder. Image. Tab to focus. Zoom out. Zoom out. Turn left. Turn right. Zoom in. Ready.
It's an example of one thing that we've been toying with. We built a different application called EasySnap that helps blind people take pictures of arbitrary objects in their environment. This is actually based off of discussions with existing blind photographers about how they take pictures of objects. The idea is basically that they will they'll take their phone or their camera, hold it up close to the object, and then move back, right? So you can get a very good sense. And you kind of saw this actually in the video with the person taking the picture of the thermostat. So we added a little bit of technological support where we basically have the user take a close-up picture, and then we use computer vision descriptors to allow them to move farther back than they would be able to with just their arm's reach. And so that's what EasySnap is, and here are some examples of pictures taken without and with. We ran a study. We had people take pictures of random objects in our lab, so blind people brought into our lab taking random pictures of objects. We actually crowdsourced whether or not the pictures were good or not, because it's kind of a subjective measure in and of itself. Taking a picture of the tea kettle, which one has the tea kettle better centered? We got okay results. We did better with feedback, right? So with EasySnap, about 57% of the pictures taken with EasySnap were preferred over the ones without. Probably a lot more room to improve there. There's one other example of how we're kind of combining this idea of human computation with computer vision. We've noticed that a lot of the questions that people ask are actually motivated by finding the right thing. So finding, say, the right can in the cabinet. So you have a bunch of cans that are all feel the same, all about the same weight. You're looking for the corn or whatever else. Or you're in the cereal aisle and you're looking for the box of Wheaties, say. We built a prototype where essentially the user speaks what they take an overview picture of all of the objects. They speak what they want to find. In this case, we'll look at the Wheaties. We crowdsource just the identification of the Wheaties. So the crowd worker just draws a box around the Wheaties. And then we build a computer vision descriptor that's specific to that box of Wheaties and that lighting and those lighting conditions from approximately the same perspective that then uses kind of a Geiger counter type of audio interface to help the user locate the object in space. And so it's kind of this neat idea where the hard part of computer vision is done by the crowd, but the really interactive piece is still done with automatic computer vision. And then you could always combine them and use VizWiz to say, find the nutrition information of the object you found. All right, so that's VizWiz. But this talk was real-time crowd support. And so that's what this next project is about, that we call Legion. And the idea with Legion is to outsource control of existing computer interfaces. So the computer interface on my laptop here or on my desktop to the crowd. And this is very different than what people have done with crowdsourcing before, where normally it's pretty asynchronous. Even our VizWiz had that delay of 27 seconds. Now we're really targeting these real-time control tasks from crowds. So crowds formed of dynamic groups of varying reliability, and somehow we need to make it so that crowds can both be in real time but also reliable. And so these seem like a natural tension, but Legion helps to make this possible. So the idea is essentially, well, it would be great if I'm having trouble with my computer. Say I'm a person who's blind and some part of my software is not accessible, or one of the things that actually motivated us was we were trying to figure out if there was a way to apply crowdsourcing in assistive robotics. So imagine controlling a robot from the crowd. And so all of these things we kind of captured as controlling an existing interface on your existing computer. And so the idea would be to have a kind of remote desktop type of setup, but where instead of having a single worker, single person controlling the interface through the cloud, we actually replace the single worker with a crowd and have that crowd collectively control the existing interface. And so really the challenge here is we have all of these people who are trying to control the interface, pressing keys, making mouse clicks, and then we have to have something that takes in all of these simultaneous inputs and figures out a way to intelligently merge them and send one single stream out to your existing interface. I'll show you an example of what this looks like for first end users. So how would you as a user set the system up? Quick little video. Oh, media not found. Oops. OK. Well, essentially what you do is you describe what you want somebody to do with your task, and you draw a box around your existing desktop to say what part of the screen essentially the crowd can have control of. And now that one didn't work. This one's probably not going to work. But this is what the worker interface would look like. In this case, we've outsourced or crowdsourced control of a webcam robot, so a little remote control webcam. So the crowd sees this view of the webcam on the robot. They're given instructions on what keys they can press. In this case, just up, down, left, and right, and space to indicate they don't want to do anything. We give them minimal feedback about...
It's 5 o'clock.
It's great technology, right? So I feel like I'm in Star Trek. Anyway, so we give them minimal feedback on kind of what's happening. So one tension here, if you think about the usability of something like this, is if there's all these people that are all simultaneously trying to control this one interface, it means that the system is necessarily not listening to everyone, right? And if you're not being listened to, then you don't get feedback, right? So if I say robot turn left, and the robot does nothing or turns right, then I might think, well, the system isn't even listening to me. And so we give them some minimal feedback about whether they're being listened to or the crowd is being listened to. In this case, in this particular case, we've set a goal, and the goal is to drive the robot into a kettle that we've set up in a little pin in our lab. And this is basically just a really boiled down navigation task. So there's a lot of great stories about what happened before we had our pin, about the robot being controlled by the crowd. Thought it was really fun just to kind of wander around the lab, looking at people and exploring. So there's other problems that happen when you include real people. I'll see if this video plays. It doesn't. I could open it up, but I think for time, I'll just wait and just describe how we do the merging, because I think that from the kind of computer science perspective, from the HCI perspective, that's kind of the most interesting thing. So I mentioned the system Legion disguises the crowd as a single user. And so in essence, what we need to do is take these users as they provide input and somehow merge that together. And so what I'm going to do is I'm going to go through 5 ways of merging this input. 5 input mediators is what we call them. And these are going to be in order from kind of dumb to increasingly smart. So bear with me. The first is we could just kind of just forward it all, right? So as people type something, we could just combine it. We just merge it into a single stream. We call this the mob input mediator. And as you expect, it doesn't work all that well because it's kind of just chaos. So this was kind of chaos because each individual had their own plan, potentially, but we were just kind of mashing that all together. So you might think, well, the other dumb thing you could do is you could just pick an individual crowd worker. And this is what we call solo. The problem with solo is that you might get a malicious crowd worker, or that crowd worker might just decide to disappear. So I mentioned that this crowd is dynamic, and so people come and go. Well, your person you picked might just leave, or they might be bad. And so that's not very smart. So one level on top of solo, which is a little bit smarter, is active. And active, essentially, we pick a random crowd worker to control the system until they stop controlling the system, and then we pick a new one. So here we picked a random crowd worker, and partway through, we'll pick somebody else. That gets us a little closer, but it still doesn't address that problem of quality. So you get a bad apple in there, upside down red guy, I like to call him. And it doesn't matter if other people are providing good input, you might have just randomly selected the bad guy. And so you might think, well, you know, the next thing, well, this is like a lot of people who all have their own ideas and they're all providing input. Well, this sounds a lot like democracy, right? So why don't we just take a vote? So we could vote, and what that means is that we actually delay our input a lot. And the reason for that is to vote, you have to divide time up into time segments over which the vote is taken, because there's no other way to easily align these inputs. And so regardless of how long this is, no input is output until at the end of the time segment. So the vote has to take place over, say, a second in our case, and output is only forwarded after that second. And so the final variation of this, which is what we called leader, use the vote not to select the input to forward on, but actually to elect a temporary leader who would assume full control. And so the idea is that using crowd agreement, we can actually select an individual crowd worker who, for the moment, seems to best represent the rest of the crowd and forward along that person's input directly. And so that means that that person has full control, but if they go against the crowd wisdom, they'd be dethroned. Someone else would be elected. And so we have this idea of kind of balancing the tension between reliability and real time. Certainly, if once somebody was elected, they could do something malicious. But we assume this won't happen because we give them no clue that they're actually leader. Now, if that always holds is a question to consider. All right, so just a simple experiment that we did. We set up this task. This looks deceptively simple. So we have this robot here on one side of our pen, and we told him to drive over to this teapot. The problem is this robot was abused by undergraduates for several years and veers severely to the left. And so it's actually very hard to control this robot. But nevertheless, we were able to take this cheap webcam robot, run-down cheap webcam robot, and turn it into a robot that basically responded to natural language commands and could be done in real time. We were able to compare our various input mediators on this robot. So this chart represents the average completion time over 10 trials for each one of the input mediators. There's several things to point out. First, solo was actually the fastest. So I was not so positive about solo, but it actually worked out pretty well, because if you happen to get a good worker, the good worker could actually complete the task pretty quick. These numbers over top of each bar, however, represent the number of successful trials. So it turns out that only 4 of the 10 trials were successful with solo. Mob was more successful, but it took longer. Vote took even longer. Active worked pretty well for this particular task, because eventually you'd find a worker that would be able to drive you to the goal. And then finally, the leader input mediator was faster than the rest and actually completed all the trials. Here's a visual of what this kind of looked like. These are just chosen to kind of be what we thought of as representative. Solo, someone gets control of it, and in this case, they kind of think they're going straight. They kind of just veer off into the wall, and then they're like, what happened, and quit. Vote, there's a lot of just back and forth about what should be done. So there's a lot of thrashing in vote, right? And then finally, they kind of figure out a good strategy and go, but it takes a while. In active, it works out pretty well in the beginning, and then whoever this is disconnects, and somebody else just thinks they're going to mess around and starts exploring around the area of the teapot and never actually drives to it. So we got a bad worker in that case. And then leader actually works pretty well, so it more or less goes toward the tea kettle. And this is kind of what we observed just qualitatively across the different trials. So this idea is pretty interesting. It allows us to do pretty cool stuff. Just one example of what we thought was interesting was it allows us to create what we call desktop mashups. So in this case, we're trying to do something very similar to that setup with the existing webcam robot, except what we've done is we've taken this little scribbler robot, which can be controlled by this terminal program here, and we've put an iPod Touch on top of it, and that iPod Touch is running Skype. And so we have the Skype program located next to the terminal program. We outsourced both of these to the crowd, and now we've taken a robot which previously could not have been controlled remotely, let alone intelligently, and we've turned it into this, again, a natural language following robot controlled by the crowd. And so this is kind of neat. So you can kind of group these applications together and create these new kinds of mashups. In general, what I'm excited about and what we're working on now is applying this idea of crowd support, real-time crowd support, to other problems. We've been looking at how the crowd can, in real time, label activities. So we have an ongoing project at the University of Rochester where we're trying to identify what people are doing in their home. It's actually targeted at providing support for people with cognitive impairments. We have an extension of VizWiz in which we're sending a video stream out to the crowd, and then we're trying to get them to basically have a conversation with the user. And what does that mean, right? So basically, can we adopt this idea of converting this crowd into a single person? Could you have a single, consistent, coherent conversation with a crowd? And in our case, we're applying that to helping a blind person navigate or understand more about what's around them. And then also in audio description, right? So we've talked about kind of description of visual information, but what about audio information for people who are deaf or hard of hearing? The activity recognition problem, we actually just last night submitted a paper to Pervasive about. And it's kind of neat. The interface changes a little bit, but it's very similar. We show workers a live video feed of what's going on, and we ask the crowd just to, in natural language, type the activities that they see. And using kind of slight variations on the same input mediators that we talked about before, we're able to kind of extract a consistent set of activity labels from the crowd. And we use those to train in HMM. So in real time, in a very deployable way, we're able to put activity recognition for tasks we've never seen in situations we haven't explicitly trained the system for. All right, so I am out of time anyway, and so in conclusion, human computation is really interesting, and I think it's even more interesting when we apply it in real time or nearly real time. This whole approach builds on how people with disabilities get answers now. It just puts them in more control and allows more ubiquitous access to that human support. Enables us to build quick deployable prototypes, Deployable Wizard of Oz, that sort of thing. And I think this idea that I talked about with Legion, where we're turning this dynamic group of unreliable people into perhaps a more reliable single user that can use our existing interfaces, is a new model for each CI that I'm excited to explore in the problems I talked about and maybe more. So thank you very much, and thanks again for having me. I'll take any questions that you have.
So I had a question about Legion. For your performance data, it seems to be that the leader seems to do things more quickly, more reliably over all the trials, right? But was there any churn in the leadership for those experiments?
Yeah, so I think on average the leader changed 3 times in our task. I didn't say how long this took. As a baseline, it took some undergraduates who we told to do this as quickly as possible, 46 seconds to drive the robot from the beginning to the kettle. And so over that time, we actually had the leader change. And it took them a little longer. You saw from the chart there, a little bit longer. So 100 seconds for the leader. It changed, I think, about 3 times, was what I remember.
I think it's a very cool idea, using the crowd consensus control. But what do you think the sort of downsides of, can you imagine any instability in this sort of paradigm, this control paradigm?
Instability in the sense of...
So, you chose a sort of a robotic example here. I think the paradigm is saying is you take these unreliable people, and they're better than any single individual to be, reliably complete the task. So your results are perfect, right? They prove your point. But I'm just saying, what's the sort of downside to this? Is it sort of, potentially it's a flawed idea, or it's susceptible to certain misbehavior?
Yeah, well, there's all kinds of limitations in this particular setup. So one is privacy, right? So you have to be pretty careful about what you actually send out to the crowd. The way we deal with this now is you get to choose the part of your interface that you send, and you actually whitelist the commands that they're able to send. The other thing, I guess, that's potential is you could imagine malicious workers somehow figuring out how to game the system, gain leadership, and do something undesirable. So there's certainly those sorts of things. I didn't talk about it here. We actually also ran a study, very similar study, and got similar results where leader also came out on top, where we took a picture of a hand-drawn table, like on a whiteboard, and we kind of we drew a picture. We drew our box around that, and also around part of a spreadsheet program. It was actually Google Spreadsheets, and we asked the crowd to transcribe the table into the spreadsheet. So it is actually robust across different types of applications, but I'm sure there's limitations, and we're only beginning to kind of explore what those limitations are and to what extent we can get around them. Anyone?
So, I guess with your VizWiz program, I'm worried. It looks like you take essentially an image and a speech recording and send it out, and the crowd returns you some sort of text or something that can be read. Or is it possible, kind of along the lines of what Professor Campbell was saying, for like a computer program, to say a screenshot of the CAPTCHA and they do pre-recorded voicing and suddenly have a way to break CAPTCHAs?
Yeah, well, so in general, that's been somewhat of a problem on Mechanical Turk. There's a study out of UCSD that showed that I think the CAPTCHA market makes it so that Mechanical Turk actually seems expensive. So there's actually CAPTCHA farms out there who will solve, I think it's 1,000 CAPTCHAs for like 80 cents or something. So it's not clear that this would be the most efficient way to do this. We have had people actually send pictures of CAPTCHAs, like from the phone, And to the best we can tell, those are actual users who have hit upon a CAPTCHA they can't solve. And so I usually solve them. But you know, there's perhaps that potential. And we get a question a lot about whether we've seen malicious users and what we would do if there's malicious users. The good side about people kind of answering these questions is that they can apply this high-level reasoning potentially to say, well, this maybe isn't the best question to be asking. Maybe you want to look at this user, and so we can block particular users, for instance, and that's probably what we would do if it seemed as though people were trying to do that.
And in the context of VizWiz, you had that Wheaties example, right, where they were trying to navigate the box. But you know, phones can do Skype or FaceTime or whatever. Couldn't you recruit a real-time video interactive or audio interactive helper?
Yeah, and so this is exactly what I was getting at with our future work. The reason we started with the first version of VizWiz with just images was actually very much a trade-off between what we thought we could actually deploy because of current bandwidth, the current bandwidth that people have access to, versus what we would really like to do. Certainly people who use VizWiz want a more interactive experience. They want to ask follow-up questions. They don't want to have to take like 5 pictures of a box before they get the right side to show the label. They want to kind of just do that in real time. So there's one hand, it was technical constraints that we didn't want to have too high of a bandwidth requirement because we didn't think that people had ubiquitous access to that. And in fact, we see it even with the pictures now. You would think, we have these, we are told that our cell connections are one thing. The thing that we observe in reality is actually much flakier and lower than that. But on the other hand, when we were developing VizWiz, we hadn't thought a lot about what it would be like to say, with my little quote here, conversation with the crowd. And so we were thinking, well, we didn't think it would be a great idea to pair a blind user with a random Mechanical Turk worker for all of the reasons that we think the solo input mediator wasn't a great idea. And so certainly we want to move in that direction, and that's what this VizWiz stream, or whatever we end up calling it, is designed to do, because exactly what you described is what blind people want, but I think it takes a little work to actually get there, technologically, and then also just figuring out the right interaction paradigm. Yeah.
I mean, the original sort of online crowd is Wikipedia, where you had some of the same kinds of concerns about in the early days of, well, if you have experts putting the content there, then it's high quality, and as soon as you don't, then you might have low quality. But the advantage there is that it's so asynchronous that over time you expect problems to be corrected or whatever. And that, at least in the short term, it seems like you could still use that. So if the person, it doesn't make it as usable, but I might be concerned if I have some concern whether it's the robot or whether it's the blind person getting a response. There might be ways to build in, wait until there are 5 responses that all say the same thing, or ways to verify the content coming back to them, that it's high quality or that it's more reliable or whatever.
Yeah, I think that there's a lot of things that we could do there. Certainly we made one choice based on one optimization of the constraints of this type of a problem, right? So our perception with VizWiz was that most of the questions we talked to blind people about who wanting to answer were of the type that we thought would be fine for them to kind of make the judgment about whether the answer was correct or not, and so that we would prioritize sending an answer back quickly versus making sure that the answer was correct before we did anything. Certainly you could make different choices, and maybe for certain types of questions you'd want to be really sure, for instance. The user can, in fact, kind of do that themselves, right? So once they get their 3 answers, they can kind of take a vote, right? So the user can actually do the vote. We've talked about other mechanisms. So for instance, what do you do when you have a bunch of workers you want to ensure are doing a good job? Well, you add middle management, arguably. You could actually have, and this is what a lot of other systems do, right? So they basically put workers in who evaluate the work others, right? And so this is a completely reasonable thing to do. We could do that in VizWiz. We could also do that in Legion and all of the follow-on projects we have imagined for that, where in real time you could actually have people observing other people's real-time answers and just kind of giving a yes, yes, that's good, or no, no, that's bad, right? And there's a little question there about what the interface would look like. How do you actually keep people paying attention and all that stuff? But certainly something that we could consider.
If you expand the size of the crowd first, though, that would be, I mean, if you expand the number of people giving correct answers more quickly, that would seem to be a first, before you have to add middle management.
Yeah, right. Well, yeah, it's hard to tell what the best approach is. The good thing is, people often think that, and I think this is getting less, but when I first started talking about VizWiz, people were very concerned that there wouldn't actually be enough people on Mechanical Turk to answer our questions. It turns out that's not a problem. We've very consistently been able to attract pretty big crowds quickly. There was a paper at WIST, actually by Michael Bernstein at MIT. He was able to get crowds of 5 people in 2 seconds. So you can get these crowds quickly. And there's all kinds of models about how you do that. Essentially, he paid people to wait. And we had a different model where we kind of queued up the workers and had them kind of iterate over old tasks. But there's all kinds of things you can do to get these workers quickly. You can get big crowds, and really the question then is, what do you do with them? And that's really an algorithm question, right? So people talk about crowd algorithms. So how do you get the best results out of these kind of noisy black boxes? And it's really how you structure that. It could be middle management. It could just be a redundancy thing. There's a lot of options.
Great. Well, I think we'll take any other questions offline.
All right. Well, thank you again.